So we're doing about temporal difference learning, and this is a kind of a philosophical question. When you're doing temporal difference learning, what order should you learn in? The late game or the early game? You guys are probably acutely aware of this. Should you teach your tic-tac-toe program like where to put the last piece in, or should you teach it where to put the first piece in? Which one should you teach it? Although I will say temporal difference learning we learned after this project, so maybe you're doing it without temporal difference learning and then you're not worried about this yet. But let's see what you guys said. What is it doing? Reveal counts. Okay, we got a 7 to 5 to 2 split. 7 people think we should learn the later values first, which is just around half the people. That is the correct answer. So if you said late stage, that's right. Does someone want to explain how they thought about it, why they chose late stage? Yeah.
It's something like during tic-tac-toe, it's very easy to know where the final stage. So those you know, and so you could do them later because then they can where you break way forward.
Okay, so you're saying I think you said a couple things. So one thing you said is they're easier. Why are they easier?
Less things to look for.
Yeah, there's like less things that are going to happen, right? Like it's near the end of the game. I guess tic-tac-toe has this like sudden ending property, but you can imagine in our game pig-tac-toe, you might even get into a situation where the game is still going, but like you already know who won. In fact, I think the first time we played, we got into that situation. You guys got a bunch of bad coin flips, and then you had like, even if you got every other square on the board, I was still going to win. So we still had like 6 or 7 turns to play, but it was sort of already over. So the late stage is easier because easier to compute what it is. That was one thing you said. Then you said something else. What was the other thing you said?
Because I guess it's when we learned that if we're starting the later stages, it's easier for the stuff to sort of like going forward.
Okay. Yes, this is a nice. So going back, let's see if I can pull up that beautiful picture from the book of the dude sending information back in time. And I guess let me try to find it with the chapters this time. Planning, approximation, off policy, eligibility traces, the lambda return, and then we learned about TD lambda, and we had this beautiful picture, right? Of this is how temporal difference learning works, because you have the future, and you're sort of sending information back in time, right? And you know what is happening in the future, because the future is close to the end of the game. So at the end of the game of a tic-tac-toe, you know who won or lost, and then what you're doing is you're sort of like shouting that information backwards in time, and you're telling the computer, that move you played at the beginning sucked, don't do that, right? Like, and of course it's too late for this game, but you're like sort of storing what you've learned in the parameters or in however you're doing your value function, and that will hopefully next time you'll learn not to do that or to do that. Not do the bad things, do the good things. And so temporal difference learning has this sort of like arrow of time, and we're learning in the reverse direction by sending information back. So you can kind of think about it like this. Okay, any questions or comments about this idea of temporal difference learning, sending stuff back in time? Okay, so I will tell you there's one thing you have to know about with respect to temporal difference learning, and I guess let me draw a little summary of this. That'll lead nicely into the next thing, right? So in temporal difference learning, TD learning, so the idea is at the end of the game, if you have this like time arrow, so here is time. So at the end of the game, things are certain, and you can calculate exactly what is v theta of s. So you find the value of every state, and you know it very well because it's the end of the game. Like there's no more choices to be made, so you should know v of theta of s very well. And then sort of in the like here's the late game. Ooh, you know what? Let's be fancy. Let's call it the end game. That'll sell lots of videos. Here's v, maybe a couple turns earlier, and then you have the mid game, and you have the early game. The opening. Okay, look at us. We're selling so many chess books. Okay, -3. So some time in the past, right? And the point is that at the end you're certain, and you should learn this very well. It should be easy to learn. And the further back you go, maybe the harder it will be to learn. And temporal difference learning is the idea that each section is learning from the next section. So to learn the end game, you learn it based on what will happen at the end. And to learn the mid game, you learn it by the end game. And to learn the opening, you learn it by the mid game. And that's because we're always using these temporal differences, like v theta of s minus 2 minus v theta of s minus 1. This is the temporal difference. and we update based on that. So whatever we think is the value of the state in the opening, we will adjust the value of the opening to be more like the mid-game, and so on. In contrast to this, if you did Monte Carlo learning, in Monte Carlo learning, you start at the beginning, you would play all the way to the end, and you learn from that. So you kind of go, like this. This is Monte Carlo learning. Monte Carlo learning. And so Monte Carlo learning is more anchored to the reality than the temporal difference learning. Temporal difference learning kind of learns from itself at different values of time. And that is why temporal difference learning is called a bootstrapping method, which we briefly talked about last time. So TD equals bootstrapping. And bootstrapping is like learn from yourself, or like something from nothing. Something from nothing. Okay. And again, TD learning had all sorts of advantages, but it is sort of like you're kind of relying on this chain to work, and sometimes it doesn't work. That is the next thing that I'm going to warn you about, is the thing called the deadly triad in the book, which is a great name. Let's see if we can find the deadly triad. Let's go back to the table of contents and look for the deadly triad. That's a lot of notation. Where's the table of contents? Okay. Policy gradient. Okay. The deadly triad, here we go. So here is the deadly triad in the book. And the deadly triad is if you have a combination of these three elements, all of which are kind of like sketchy, together they can really mess things up. So our discussion so far can be summarized by saying the danger of instability and divergence arises when we combine these three elements. So when you're trying to learn something, it might not work. So far we've been doing things that are safe. So Monte Carlo learning is safe, especially if you have a linear value function that's linear in the parameters. That's another level of safety. But these are the three kind of things that together can lead to things going wrong. So function approximation, right? Instead of looking up the values for each one, you have these parameters and you're trying to learn them. So of course it's very good and it's very powerful and it's super useful, but you gotta be careful with it because it can do wonky things. Bootstrapping is the other one. So in bootstrapping, you don't learn from the true value, you learn from yourself. Well, you better hope that yourself is at least learning a little bit, otherwise you're learning garbage, like garbage in, garbage out. So update targets that include existing estimates, as in TD methods, rather than relying exclusively on actual rewards, as in MC methods. So MC methods, in some sense, are more like anchored in reality, and they will not like daydream and make stuff up the way TD methods sometimes will. And last but not least is off-policy training. So that's training where you're learning about a policy other than the one that you see, right? So you see one thing and you try to extrapolate from what you see to what you're actually doing and try to figure out what is good or bad for you based on what you saw. The combination of these three things, each of which on their own is sort of like maybe possible to work around, together they can lead to bad things. Right, and in TD learning, what will happen is, because of this bootstrapping thing and function approximation, what will happen is your algorithm might start to daydream about the values of states. So let me open up my picture. So imagine, I'm trying to learn I'm quite certain at what happens at the end of the game. So my value function at the end game is learning from that, and it is doing well. But you might imagine when I first start playing that everything is just purely random. So what I think is a good opening or a bad opening, it depends on what I think is the mid game, but that was perfectly random. So at the beginning of the game, maybe we start doing some really weird stuff. And if you don't deal with that, this weird stuff can sort of exist forever if you get trapped in certain ways. If your function is complicated, and it might never go away. You might never learn the opening correctly through TD learning. So that's something to watch out for, and that's why it's sort of nice to start with Monte Carlo learning, because it's sort of easier than TD learning. Like TD learning is like advanced Monte Carlo learning. Okay, so that's a warning about TD learning. And I will tell you though, there is good news. Can anyone think of a way in a game like tic-tac-toe or a game like pig-tac-toe, how could you help anchor the TD learning in reality and make sure it doesn't start daydreaming and sort of like going off the rails for the early games? So remember I said, I used the words opening, mid-game, and end-game, and I was like, we're gonna sell a lot of chess books. So if you're not in the chess universe, there's like lots of courses you can buy online, like how to play the French defense. You pay like $100 to like learn like a really good opening. Yeah.
Do you hard code in certain beginnings you know are good?
So that's one thing you could do. I do want the computer to learn, because it's a game that I don't actually know what's good or bad. So I don't know what opening is good. And unfortunately, there's nobody in the world who knows pig-tac-toe because I made it up. So you guys, you will not actually be able to find a course on pig-tac-toe. But there's something else you can do. Yeah, are there any other books you could buy?
No.
Stockfish only works for chess. Yeah, that's not pig-tac-toe, unfortunately. Yeah. So how could you anchor your algorithm in reality and make sure? Yeah.
Would you just like start with Monte Carlo and then switch?
Yes, that's a great way to do it. So start with Monte Carlo, and then you sort of like learn a little bit, and you're like on the right track, and then you switch to TD. So that's definitely one thing to do. That's like starting with an algorithm that is more stable. You could even start with a small algorithm, and then you could use the small algorithm to train the big algorithm. Some people call this a teacher-student setup. And actually, these teacher-student setups, nobody really understands why they work so well. So if you take a really, really big model and you train it on a lot of data, and it's really expensive and it takes forever, but then you train a small model not on the original data, but on the big model, it does better than it would have done if you were training it on the data itself. So that's called the student-teacher setup. That's one thing you can do. And start with Monte Carlo. So here are some ideas. Use teacher-student setup. That's a nice idea. And actually, the idea I'm thinking of is like teacher-student, but in a very specific case where the teacher is very simple, which is in between playing games and learning. So I'm gonna have my algorithm that's gonna learn with TD learning. And to keep it from hallucinating, in between every game, I'm gonna play just a bunch of end games. So I'm just gonna I'm like, now you study only end games for the next hour. It's like I give it an end game book, and I say, just practice these end games and do it. So the way I would say this is, it's kind of like a teacher where the teacher is only doing the thing. So anchor in reality by choosing states we know well. So in other words, like the problem is that the opening is sort of too hard to learn all at once. So I start with the easy positions where you can learn more easily, we know the answer. Learn those first, and then learn everything else. So let me show you some output. I was working on pig-tac-toe last night. So this will be like the bot that you guys will play on Gradescope. Let's see if I can find it. So here it is. It's called Agent Pig-tac-toe. Oh no. Okay, here it is. Okay. And here was it learning. So I ran it overnight last night. And it was learning to beat the random AI. So here is the training. And it is, so it ran for like an hour. But yeah, here's a little output of, this is at the end of training. Let me see if I can go to the beginning of training, because that'll be exciting to see the numbers go up. Okay, yeah, great. So I started training it. I had already trained it on some other stuff, but its win rate was 0.6 against the random AI. And this is the win rate in the universe where +1 is a win and -1 is a lose. So if you want to convert it to out of 100, that's 80 out of 100. So it's already pretty good. But the reason it's pretty good is because I trained it a lot on endgames before this. So it knew for any given position where all the pieces are filled in, I fed it like hundreds and hundreds of random positions, and it was only off by 0.05. So it sort of was really good at endgames when I started training it. But kind of like medium at playing the beginning and the opening. And I tried training it only, I tried taking it like this, starting it off with this thing, and just saying, go crazy and play, and it wasn't working. So this is TD learning, and it was starting to go off the rails and lose reality and just start making stuff up, and it would start to do badly. But I found I could anchor it in reality by doing endgame training. So it would play against the random AI, and then it would learn endgames. And then it would play against the random AI, and then it would learn endgames. And over time, it got better and better. So it started out with a win rate of 60%, and that went up lots. Okay, it's like a little disjointed here. Here it's 65%, and by the end, I think it briefly went above 70%, which is like an 85% win rate, and it's getting better at the beginning, but worse at the end games. But I found by feeding it end games at the end so you play a regular game, then you learn some end games, that keeps it from losing itself and going crazy. It must kind of stay, whatever it learns, it must still know at the end of the game what's a winning position and what's a losing position, because I forced it to do that. So that was how I stabilized it, and it has an 85% win rate against the random AI. I also kept things simple. This AI does not choose whether or not to roll again or not. So it always rolls again exactly one time. I haven't done that yet. And it's TD learning. So okay, so that's some stuff on TD learning. This is the kind of thing you guys will do for the final project. Yeah.
So how would you implement that?
How would I implement what?
The first playing normal, then end game.
Oh sure. Okay. Yeah. You want to peek at the code? So yeah. So there's a loop. Let's show you the loop. So this is the loop of the playing the game, and then I have this little thing I added where I do TD learning. So what is it doing? So first of all, I only ever learn if the number of pieces played is greater than or equal to 3. So I said, don't even, if it's like the first couple moves of the game, don't try to learn anything, because that's the most unstable part. So I was like, look, we're not going to learn anything there. If you want to learn something from there, you got to learn it from a different situation. So I only would learn things if 3 or more pieces were played. Here I calculated the gradient. This is exactly the TD gradient function. And I was only learning in the situations where the condition is true. So here I did some kind of average to say like average over all the situations with conditions. Do the value. I fed in the board. I also did something very simple. You might notice there's a jnp.abs of the board. So some people maybe have looked already at the code for the final project. If you haven't looked at the code, you will have no idea what jnp.abs. Why am I taking the absolute value of the board? But if you have looked at it, you might know what the absolute value is. Does anyone know why you do the absolute value of the board? I will tell you. So in Pig, there's 2 types of pieces, right? There's your actual pieces and your potential pieces. The potential pieces are stored as negatives. So if you have a -1 on the board, that's a potential piece. I made my value function. It was like, it only ever operates on one type of piece. So I take all the negatives, I turn them into positives, and I say, if I was to freeze this and turn all the potential pieces into real pieces, how good would that be? That's the absolute value. Okay, so then I add up the gradients. So I have this function that accumulates the gradients. Actually, I'm going to talk about this later today, so or maybe next class. But this is just adding up the gradients as you go. So instead of doing updates all the time, I just do one big update at the end, and I add up the gradients as I go. And then at the end of all the games, I also do the end game training. Let's find the end game training. So this just finishes simulating the games. And then I have this little end game training where I take 100,000 games and I make 100,000 random end games. So I take a board and I fill it with X's and O's in a random way 100,000 times. And then I tell the computer, you better learn the value of this thing. It's just like we were learning before. I add on these gradients to try to tell it, move your value function towards the true reward over here. So it's 2 steps. What is the gradient from the games? What is the gradient from the end game? And then I update it once. So I do the updates one time to do one big update, change all the parameters. So it's trying to do 2 things at once, trying to get better at the game and trying to remember all the end games. It has to do both. Yeah, great question. Okay, so that's like one like life pro tip, and we're gonna do some more of those today. All right, yeah, any other questions or comments? Okay, so that's it for sort of TD learning. So let's do a quick little recap of TD learning, right? And of course, you don't need to do TD learning. You could do everything with Monte Carlo. It's just that TD learning is nice because you don't have to store as much stuff. You can make things a little bit faster, and so on. So it's your choice what you want to do, especially for tic-tac-toe. Monte Carlo learning is more than enough, and TD is kind of overkill. Okay, so what have we done so far? Let's do a quick little recap of everything. So we learned about the value function v and the q function q and the Bellman equation, and that is like the basis of everything. And we started sort of in like math land where things were very nice and there were matrices and we were like talking about, oh, you like multiply this matrix. But then we wanted to learn without the matrix M, right? You don't know the matrix M or it's too big to write down. The number of states is large, so the number of entries in the matrix, the number of states squared, is even larger. So that's when we did Monte Carlo learning. And we introduced parameters. Oh, and one other important thing, before we did parameters, we talked about this explore idea, and that was our epsilon greedy. That's another important thing that can go wrong that we saw. Explore, I'm gonna call this explore versus exploit, right? Should your AI always play the best possible move, whatever it thinks is the best possible move, should you always play that? Well, if you did always play that, you might paint yourself into a corner where you're not trying enough stuff, so you're not learning. So you don't always want to play the best possible thing. You want to do some exploration, and that was our epsilon greedy. So that's what we had so far. And then we were, basically this is like the core of how the algorithms work. And then we're talking about upgrades to these things. So one example is we upgraded Monte Carlo learning. We upgraded that to TD learning. It's like an upgraded version, and it has some caveats and it's harder, but it can be a lot better. It can be faster, and it can be more sort of efficient. One thing we are going to learn sort of next as our next math upgrade, we're going to learn how to upgrade the epsilon greedy. So we're going to have something else that you can do that's fancier than epsilon greedy. And it goes by the name bandit problems, which is a cool name. Bandit problems. And we're going to start that soon. But today I actually wanted to keep things on a very like down-to-earth level and not talk about, these are sort of like theoretical like math upgrades. I want to talk about a very practical upgrade, which is what I call vectorization. So this is like we put on our computer science hats, and we're going to talk about vectorization. And this is trying to do the same kind of stuff we've been doing, but do it all in these big batches over vectors. And that's much faster and much more efficient. And this really changes the game on like what possible games you can solve. So like tic-tac-toe, your assignment that's due soon, that was designed so it's small enough, even without vectorization, you should be able to solve it just the regular way. But if you try to do pig-tac-toe and you don't do any vectorization, I think you will have a really hard time just because it will take forever. So for example, when I was teaching my agent the other day, and there's lots of things you could do to simplify what I did. But this agent, it was doing 100,000 endgames at once, right? And you can do 100,000 endgames in like a couple seconds because it's vectorized. If you tried to do 100,000 endgames one at a time, that would take like, maybe like 20 minutes just for one run of this. And I did it 1,000 times, right? So it really changes what you can do. I was also, how many games was I playing at once? I was playing how many games at once? Let's try 5,000. So not really that many. But 5,000 games, I think it took like 10 seconds per run. So that's running the 5,000 games, play all the games, do those 100,000 endgame puzzles at the end, do that 1,000 times. So altogether, we're in 5 million games. This took about 1 hour on my MacBook. If you tried to do it without vectorization, I think it would take like a week or something. And then you run it for a week, and then you're like, oh, it's not very good. So you really want to have it vectorized, and if you have things vectorized smart, you can run all the stuff in like an hour or something, and it will do what you want. So that's what we're going to learn. We're going to learn this vectorization stuff next. Okay. So yeah, that's the little game plan. We're going to do some practical vectorization stuff. I'm going to show you a cool function called jax.vmap that does some vectorization for you. And it should help you out with some of these things, and it will definitely help towards the final project. But before we jump into that, any overall questions or comments or anything else? Okay. Let's jump into this. And so I have a little starting puzzle for you, which is a fun sort of starting problem, which I call the pairwise difference problem. Pairwise distance problem, rather. So you have a bunch of coordinates. So you should think of these as like a number line. So we got like x1 is over here, or I guess x0, and x1, and x2, and they're all living on a number line. And this is actually a common thing you might need in real life if you're playing like a video game or something, or in some data science methods. You want to know how far apart is any pair of these. So you want to make a matrix so that like m01 is how far x0 is from x1. How far apart they are. And my question to you is, how would you make this algorithm? Like, how would you program the computer to do this? What's the most efficient way you can think to do it? You can just describe like briefly how you would do this. Imagine you're given this vector and you're asked to do this. What do you think? I'll let you think for a minute or two. Try to think of how you would calculate this matrix. And yeah, I guess you have to take my word for it. The matrix is actually useful for a bunch of things. But I'll let you guys think for a couple minutes. there's like 20 seconds left. Put in whatever guess you have. It's totally okay if you don't know. You don't have any ideas, that's fine. Just trying to get a sense of what you guys are thinking. Yeah, and again, if you've been, depending on how hard you went on this tic-tac-toe thing so far, you might have learned something in the last week that would help you with this. Okay, let's take a look at what you guys think. We got a word cloud, the. All right, the. Okay. Oh yeah, okay, this is nice. The one thing to notice, it's symmetric, so you only ever need half of them. That's very nice. So if you have some way to calculate half the matrix and then flip it to the other half, that will be very nice. You'll sort of have a savings of ×2. This is a very common thing that you notice these savings. Sometimes the savings are overruled by just doing something that the computer likes. And you're gonna see the thing that we do is gonna just calculate all of it all at once, automatically. And I can't think of a way to actually use this for a real speed up. But okay, it's a good idea. Okay. Ooh, 2 variables that contain all the indices. Yeah, this is a nice idea. Yeah. Okay. So I think you can do this. Okay. So my plan was to just open up a new collab, and I have some hints. I have some hints for myself here, if I need the hints. But let's just open up a new collab, and go from here. So we're gonna import numpy as np as we always do. This is the chant we always do when we enter a room, and then I'm going to make some random things. So x is np.random. .randn, and this Google is suggesting 8. Let's make a variable for that, n size. Okay. N size has to be, let's make it 3 for now, so we can plot things on the board. Okay, and then I think one thing you can do, ij is going to be np.indices of n size. And did I spell indices wrong? Yes, indices, one of the hardest things about programming. Okay. All right, so this gives me these array mi, and then I think you can do m of ij is xi minus xj, and I think that will work. Wait, with an absolute value. Okay, you gotta do, and well, let's just do the difference. So who can predict what will happen when I hit run over here? Who thinks it will work? Who thinks it will not work? Who thinks it kind of works, but there's a stupid reason that it won't work? Yes, okay, that's what's gonna happen. Hey, what the hell is m, you moron? Okay, yeah, okay, m is np.zeros of the size we want, and then it should work. So you gotta tell it what is m, and then I think this will actually work. So this is a very, very clever idea. N size, yes, thank you. Okay. Okay, let's print m and check it out. So here's x, not with capital. And here is m. Okay, so first of all, the diagonal is all zeros. This one is asymmetric because it's the difference. When we take the absolute value, it'll fix itself. The difference between negative 1.46 and 0.59 is indeed negative 2.0 something. So that actually works. This is very, very good and very nice. I have no idea how fast this one is. So the classical way I was doing it, let's see if did anybody write for loop? That's the way I would think to do it. Iterate something, check the difference. Ooh, yeah, prefix sum. It doesn't. Yeah, I was gonna say I don't think it works. Okay, yeah. This prefix sum is like a common trick in these leet code type problems, but I don't think it applies here. Ooh, this is nice. So you do it row by row. This is one thing. So if you do a for loop, you can try to do it with one for loop and do the full row rather than do 2 for loops. But this is the most innocent way to do it, is to just do 2 for loops. So 2 for loops. So here would be the that way. Let me take this one and put it in over here, and then I'll make a new solution as the for loop solution. So we just do for I in range, n range, and then I guess if you want, you can try to be clever. You start at I to n range. Huh?
Why n range? Not the n range. Shouldn't be
Oh, n size. Yes, thank you. Of course. Yes. Okay. n size. Okay, so let's do this. Let's just do the differences, and then we can always take the absolute value at the end. And once again, you better tell it what m is, or it's going to yell at you, which Google nicely hints at over here. That there's a nice underlined m. Oh, if you press the power button on the screen, that's also not good. Okay, well, we'll wait for that to reboot. Okay, so let's run this and see. So hopefully this outputs the same thing. M. Ooh, okay, yeah, we only did the top half. Okay, great. That only does the top half, so we get a little savings. And here's the fun way you can do this % time it to see who's faster. All right, and I'm gonna tell it do one run. I think I do this and one. Is that a thing? Yeah. Okay. So this tells you how long it took. So which one was faster? This one took 800 microseconds. This one took 34 microseconds. But the interesting thing to see is what happens when you make the n's bigger. So let's make n 1,000 and try it again. So you gotta type in. Yes. Look at that error for just missing one letter. Brutal. Okay. How long does it take? So that took 346 microseconds. And now this one's faster. So I do think this one is faster for large n values. And I think the reason it is slower for extremely small values is you do have to create some more stuff. So you have to create this ij, but otherwise it's pretty good. So whoever thought of that, that is very nice. There is an even faster way to do it, and that's what we're gonna learn today. So it's called broadcasting or vectorization. And what you wanna do is you never want to, whenever you have to think of a matrix, you think of vector operations that can combine to make it. And kind of what this is doing, if you look at x of I on its own, so in this little universe, right? We had x, and if ij is like this, what is x of I? And I guess an easy way to do it, let's ask it for its shape, x of I dot shape. So x of I dot shape is a 1,000 by 1,000. Why is it a 1,000 by 1,000? Well, when you make ij, when you do this, ij, they're both n size by n size, and they're the arrays of size 1,000, 1,000, where I is the I axis. So actually an easy way to see it is, let's go back down to 3, and let's try this again. So x of I is a 3 by 3. What is just I? Tell me, what is just I? I is this thing. Zeros, ones, twos. And then what is j? I gotta start adding print statements. Let's do f I equals. Okay, so that's I. Here is j, right? It would be the same thing, but the rows and the columns are flipped, right? So I is like, it's the matrix whose entry is I. Like it's solving the problem mij equals I. That's what the indices mean. And same thing with mij equals m. And so last but not least, what would happen if you do x of I? Well, then you get the array. You get the 0th entry here, here, here. You get the 1 entry here, here, here. You get the 2 entry here, here, here. So that's xi. And then here is xj. It's the same thing. Okay, so this indices solution, what it is actually doing is you're taking these arrays that are like pre-built of the things stacked the right way, and then you're saying like, extract the values of x that match these indices. And then it makes these copies of themselves. And then when you subtract them, it does exactly what we want, right? So like, if you subtract this one minus this one, well, this is the these are the copies of x1, these are the copies of x0. So if you subtract this row from this column, in this entry, it's x1 minus x0, which is exactly what we wanted. So that's why this thing sort of works in a lot of detail. And doing xi minus xj, very readable, but you can do it a little bit faster by just telling the computer, just make these arrays by copying x many times. It's faster to copy the numbers than to get these indices and then plug them in to x. So how are we going to do it? Well, one way is to use a very readable way to do it, is to use something called inops. So we're going to import. So from inops, import, and I think we want rearrange. That's the one we want, rearrange. Let's import the other ones as well. I don't know their names, so I need Google to tell me. Reduce. Okay, find Google. I'll make them up. I think those are the one. I want repeat. That's the one I want. Okay, great.
I was gonna say they're on assignment 4. So
They're on the assignment. Yeah. So these are very readable ways to do operations like doing x of I But if you do it with inops, it does exactly the same thing. It's just nicer. And so here is the nice way to repeat the x a bunch of times. So I'm going to make a new copy of x of I, and I'm going to call it, like, if you want, I can call it xi. And what it is, it's just repeat x. Okay, I'm going to let's call this. Okay, Google, you've done too much. Okay, x. So we're going to call this the n-axis, and that goes to the n-axis, comma, new, and new is going to be repeated n size times. So when you do these inops commands, you have to write in sort of like English words. Well, not quite English, but in symbols, you write a string with the commands that you want. And what this is telling it to do is it is telling you how to convert the x vector. So we're going to repeat the x vector. How are we going to repeat it? Well, we're going to first label the original axis as the n-axis, and then we're going to make. So that's the input on this side of the arrow. On the output is the n-axis, and it's copied over new times, where new equals n size. And so what this will do, this should look exactly like the xi we had before. So if I print f xi equals, it should be the same exact thing. It's just copied itself over a bunch of times. And it should be a little bit faster to make this xi than it is to make the x of square bracket I. Because we sort of never need to do any lookups, we just like do straight copying. So this is how the syntax works. So you could call this n-axis thing, you could call it anything you want. You could call it like blah, and that would say just whatever it was. The new axes of this xi, it has the 0th axis is called blah, and the first axis, like the second one over, is called new, and new is n size. You can even do this, and this will say whatever it is, could be anything. So ... is a special command that means take all of them and copy them over new times. So we copied something over a bunch of times. That's the xi. On the other hand, there's the xj. Let's put this one back the way it was. Let's call it. I guess if that one's new, this is the original axis. The original axis. Okay. Let's do the xj. So I want this one to be xj. Let's delete this. This is going to be different. Xj. So here we copied it. We copied it over. For the xi, we copied it over by doing a bunch of copies. But for xj, we want to copy it the other way. How would I type in the string to copy it the other way? Yeah?
Orig, arrow, new orig.
Yes, exactly. So orig, arrow, and then new orig. So what this is saying is the input is still one axis, and that axis is called original, and the output is going to be new, original. So this will write them the other way. So that's xj. Okay. Okay, I keep hitting the caps lock key by accident, which is unfortunate. Okay, so that's the xi is copied one way, the xj is copied the other way, and then the matrix we want is the difference. So m equals xi minus xj. That will work, and we're done. Yeah?
Would it save time to, instead of computing xi and xj, just computing xi and then doing xi minus xi transpose?
Oh, you could do that. Yes, that would be fine. I will say again, transpose makes perfect sense in like linear algebra class where you always have matrices with 2 dimensions. I will say the inops is very useful for that as well. So if you were going to do that, I would do it like this. I would say xj equals, and I would do rearrange xj, and I would rearrange it exactly as Google is suggesting over here. Xj, yeah, like that. So xj was new original. Wait, okay, Google, you're being so silly. Okay, xi was original new, and then I want to transform it into new original. So that would accomplish the same thing. And mathematically, this is transpose. Once you start to get into tensors with like 3 or 4 dimensions, you never want to say transpose because you're just going to confuse everyone. So again, if you want to do it, this is a smart way to do it. Okay, so that is a nice fast way to do it. Let's time this one and see how much faster it is. And I'm genuinely unsure which one will be faster. So I guess we're doing the differences. That's fine. Give me this time thing. And you'll notice another nice thing about this is I never had to define m beforehand, right? I didn't have to define m as all zeros and then fill it in. It just gets filled in immediately with what it is. So let's time this one and see. Okay, I guess I got to make things fair. I got to make them all the same size. Let's try 1,000 again. 1,000. Okay, so 4 loops takes 218 milliseconds. This way it takes 17 milliseconds. This one takes 4 milliseconds. So there you go. Factor of 3 speed up. Yeah.
Do you check the transpose methods? Or
Yeah, let's try the. You want to try the? Let's do the transpose. That's a good question. I wonder.
Also, you got.
I have a typo. Yes. X I. 9 milliseconds. That one's not as fast. Okay. Well, okay, this is why it lets you do it a bunch of times. To really make it, okay, let's get serious here. Let's bump it up to 10,000 and see how long things take. Because when you do these small ones, it's kind of slightly random. So this one, the 4 loops, to do 10,000 really takes all day.
Also, does it matter when you dial 1,000, 10,000? Does the underscore matter?
No. The underscore is just there for human readability. Geez, I thought this ran in 3 seconds, but now I'm realizing it might run in 3 minutes. Okay, we're gonna stop the 4 loops.
You like 5,000?
We'll do this, and then this one, and with 10,000, how long does it take? So it took 4 seconds, and this one took less than 1 second. So yeah, this is pretty good. Just under 1 second. If I do it the other way of just writing it out twice, how long does this one take? Even less. So the transpose apparently not as good. Surprising. Okay. All right. That's a great thing. So this is called vectorization. Very nice. This is the part of the infomercial where I say, but wait, there's more. So here we repeated it. What if I told you there was a way you could repeat it and make it even faster without having to actually repeat it? So this is like what we want it to do. Like we don't actually want to repeat the xi. We just want to repeat it for the purpose of this calculation. And that is baked into the computer already. So there is this convention in NumPy and in JAX and in all the machine learning libraries called broadcasting. And so this is the page on broadcasting. And what is broadcasting? Broadcasting is literally, it is just a rule that says if you try to do something with 2 arrays and the size of one of the arrays is exactly 1, then copy it over. So if you try to do 1, 2, 3 times a vector with just 2, then it will, by default, copy out the 2 3 times, and then multiply 1, 2, 3 by 2, 2, 2 to get 2, 4, 6. So what this is saying is, you don't need to waste your time writing out repeats. You can just make it, if you make it have dimension 1, then it will automatically do that for you. So what would this look like in our situation? Let me show you in the code. It's going to look exactly the same kind of as this. So let's copy it over. And what you're going to do is instead of repeating it, I'm going to rearrange it, and I'm going to replace the new with just a 1. I'm going to do a 1. And what this says is just make a new axis of x. So x before was a vector of size n, and now it's a vector of size n, 1. And then xj will be the same thing, but it'll be 1, n. So 1. I think you could technically do a repeat, but I know for sure it works with a rearrange. In rearrange, the only number you're allowed to type in is 1. And it's exactly for what we're going to do over here. So what this will do is it'll make first xi and xj. Let me show you what it does first before we time it. And I really shouldn't call them xi and xj. Let's call them x. I'm going to call them x broadcastable left. I guess this one's right. And this one is x broadcastable left. And these just look exactly like x. So if I do and I print them out, you'll see they look like, if you print them, they don't look any different than x itself. Oh, I suppose x is a long list of numbers now. But one of them is very explicitly a row vector, and one of them is very explicitly a column vector. And they actually have dimensions with an extra 1. So let's check will this work for me? Sometimes this doesn't like me. Okay, today is one of those days, I guess it doesn't like me. Okay, so you have to believe me, it's original by 1 and 1 by original. I guess I could print their shapes. Dot shape. I know I'm making a big jump up and down about the shape, but the shape is important. Okay, so one of them is 1 by 10,000, the other one is 10,000 by 1. And the rule is, the broadcasting rule says, normally if you tried to subtract these two things from each other, it wouldn't make sense. You're subtracting a row vector from a column vector, What are you, crazy? But the broadcasting rule says whenever there is a 1, that means you copy it over to match the other side. So what's going to happen is when I do x broadcastable left minus x broadcastable right, it's going to say, hey, look, there's a 1 there and a 10,000 there. I'm supposed to copy this over 10,000 times. So it's going to effectively, when I go to subtract them, it will effectively do this copying for me. And it'll do that in both axes because one of them has a 1 here and the other one has a 1 there. So it's going to copy this one 10,000 times and that one 10,000 times. So if I do it, x broadcastable left minus x broadcastable right, that will give me a matrix M, and the matrix M should be the shape that we want. So print M dot shape. Okay, so you see it worked. 1 by 10,000, 10,000 by 1. They combine to give it 10,000 by 10,000. This is called the array broadcasting rule, and this is even faster than copying it. So if we time this, this should be even faster. Let's time it and see. Okay, you gotta get the print statements are by far the slowest thing in this code, so you gotta make sure you do that. And you see it's faster by another factor of 2, so 731 milliseconds versus 381. I need to know for interest how long this thing is gonna take. So let's scroll there. And then actually here, let's open this up in Mathematize. I made a fun question. How many times faster is the array broadcasting than just the for loop solution? So we kind of did 3 levels of upgrades, and I think the array broadcasting is the fastest possible one. I guess I'm basically asking you how slow is the for loops. But yeah, was there a question over here as well? Yeah.
So how is the computer copying them over in the broadcasting faster than it copying over in the setup?
Yes, that's an absolutely fantastic question. So when you copy them over, you are actually copying them over, and you're telling the computer, I want some memory, set aside some memory for me on the computer, and write down this thing copied down a bunch of times. When you do the array broadcasting, you're telling the computer, I would like to do this operation as if it was copied. And the computer will do the operation as if it was copied, but it won't necessarily actually copy the values. So it doesn't actually allocate the space to copy the values, it just like calculates on the fly. It's like x500 minus like x200, like it just does the calculation, but it doesn't, it's like you don't need this intermediate product, so I'm not gonna waste time writing it down. And that's why it's a little bit faster. So it's doing the same thing as the repeats, but it's faster. So when you can do it, it's great. Okay, last person, put in your, I think there's like 2 or 3 people left. Put in your guess. I'm gonna stop it at 1:30. It's just for fun, obviously. There's no right or wrong answer. Well, I guess there is a right answer, but we'll find out what it is. Okay, I'm revealing. Okay, 10, 100, 1,000, infinity is not infinity. Okay, I think I talked this up too much. These are all too big. Okay, let's see. Okay, how long did it take? Is it still going? It took 25 seconds. So 25 seconds for the for loops, and the thing took 381 milliseconds. So 24.5 divided by 0.381. So 64 times faster. If you bump it up, it will get even faster. So the sort of the bigger the array is, the slower the for loops get. And you'll remember we only actually did half of them here. So depending on how you do it. So if you bump this up to like 100,000, then this can go up to like 150, 200 is pretty common. I will say, if I bump this up enough, if I go like 100 million, what do you think will happen when I run this thing? Okay, first of all, it takes a long time to make the random vector x, but what do you think will happen when I run this? Yeah.
I was saying, a millisecond is not.
Oh. Yeah, so it's 380 microseconds, or milliseconds. So I put 0.381 seconds. Is that not right? Okay, this is a good point. Let's do it. Let's do it proper. This is how you always convert things. You go to 24.5 seconds divided by 381 ms, whatever an ms is. Okay, there's a guy at 16. Wolfram Alpha confirms after doing the digits that 64.3. Yeah, so, I feel like we live in a world where being 60 times faster feels like, 60 is not a huge number, but that's like crazy. Like instead of spending an hour doing, like the thing I ran last night overnight took an hour. If you make it 60 times slower, then it takes 3 days. So like that's the difference we're talking about here. Your code runs in an hour, you like go get a cup of coffee, you come back, you have a nice time, you find the bug, you're, I forgot, I spelled indices wrong, you fix it, you rerun it, versus you run it, you come back 3 days later and you try again. Like that's the difference we're talking about. Okay, great questions and comments. Okay, so What else to say? That's array broadcasting. And so if you look at the code for our game, there's the next thing that's going to come after tic-tac-toe is there's going to be a vectorized version of tic-tac-toe, where you run the code, not just one game at a time, you run it 1,000 games or 10,000 games at a time, and it all works by this vectorization. So I'll show you that in a second. Yeah?
Also, what were you going on about the 100 million thing loops and that you had and then set it?
Oh, yes, this is a good point. Yes. Okay, so what's going to happen is it's going to crash. So if you run it, it's going to say, unable to allocate 70 petabytes.
I think that's
So it's saying you cannot make an array that big. You cannot make an array that big. So this is the one downside to this vectorization, is we're sort of relying on storing everything we want to do inside a big array. If you make it too big, it will take up more memory than your computer has, and then it will crash. So in practice, what you do is you make it as large as possible. So figure out what would crash your computer, and then back it off a little bit, and then make it as large as you can, and then do things that way. So like a good example is when you're learning these games, run as many games as you can at once, and then just like repeat doing that for as long as you need to get to the number of games you want. So this is a good lesson. This is the one advantage of the for loop, right? So the for loop, I can't store it in the matrix M because like that will take up the same amount of memory, but I can calculate xi minus xj over all the I and j, no matter how big I and j are, just by making it really big. So if you start to get above a certain amount, you need to sort of start using for loops again, but you want to take up as much memory as you can before you do that. Okay, so I think the thing I wanted to show you guys was how you vectorize tic-tac-toe. So of course, in the final project, we've not vectorized tic-tac-toe, we have vectorized pig-tac-toe. But if you understand the tic-tac-toe from doing the assignment, then this will make more sense to you. So the idea is, in tic-tac-toe, we had board, which was one 3x3 board. Now we have two 3x3 boards. So there's boards with an S, and the first board is here, and the second board is here. Let's run some of these so you can see what they're like. Okay, and so, yes, okay. Is it going to say, I don't know what anything is? Okay. Let's run before. Okay. How many games I'm running here? One. Okay, good. Okay, so it's going to run everything. But so this is the idea, is we're going to take all of the stuff you guys have been doing in the assignment for one board at a time, and we're going to just like boost it up to several boards at a time. And you're going to see there's a fancy function called vmap that helps quite a lot. So okay, there we go. So there's boards. And if I say like boards, if I say print boards, then it's gonna be print all. It's gonna print both, and then like boards of 0. That's like what you guys have been doing. It's a 3x3 thing. You could run all your code. You could say boards of 0, boards of 1, and then you could do everything in a for loop. But we're gonna learn how to vectorize it. And the first very nice thing is all of the code that I wrote, all those like helper functions, I wrote them in a way that they already work. So if they already have the ... dots in the right place. Whereas if you have boards like this, you can run all sorts of things. So for example, you can say which 3 in a lines. So you remember, if you run which 3 in a lines on a single board, so boards of 0, then it'll give you an array of which 3 in a lines are there. So boards of 0 is true, true, false, 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 true, true, false. So boards of 0 has a 3 in a line. Oh, okay. I guess I want. Let's do them for a specific player. Let's do for player 1. I do the same thing for all of them. So this is talking only about player 1. Player 1 has a 3 in a line right across the top there. So his first one is true and the rest are false. And player 2, we're not even talking about. But if you do which 3 in a line for the boards, it just automatically does it for both games at once. Let me do this so we can look at these games. So I think I want this. And let's remove that. Okay, so there are the 2 boards, and player 1 in the first board has a true in the first one, and in the second board, there's a true in the fourth one. So it just automatically works. It does it automatically on 2 sets of boards and gives you the answer. Okay, so that's which 3 in a line. You can do same thing for any. So any 3 in a lines. It'll do the same thing. It's like, look, player 2 has something in both. Sorry, player 1. If player 2, then they would be false true. Player 2 doesn't have a 3 nor here, but does have a 3 nor here. And you might ask, how did I do that? Well, when I was doing the commands, if you look at the code, they have array broadcasting built into them. So where are the things? So which 3 in a line, you'll notice it has these broadcastables. It's adding, exactly doing like we did before, it's adding this 1 in the right spot. And then it's doing these commands, like taking the 3 in a line mask that fits right here at the end and broadcasting it to the right size. So that 1 is going to copy over to the 8 in this next line. That's how it works. And the ... is handling, you can have as many games as you want hidden in the ... and it will be okay. So yeah, it's using array broadcasting. I guess, okay, it's using a part of array broadcasting that I haven't told you yet, which is I told you if a 1 is there, it copies it. There's also a rule that says if nothing is there, it also copies it. Let's find an example over here. Yeah, here's an example. So if you take 256 by 256 by 3 and you try to crunch it with a 3, then it will copy it over. So it treats 3 as 1 by 1 by 3. It always adds on 1s to the front until they're the same length and then tries it. Yeah. Yeah, so this is another rule. If it's a 1, that means copy. If there's nothing there on the left, that also means copy. So it always does this. And that's what happened over here. So in my thing, I took the board, I made it broadcastable by adding a 1 in the right spot. And then this 3 in a line mask is 8 by 3 by 3. And so it copies over this 1 into an 8, and then it does this OR operation on all of them. Last but not least, I'm doing this reduce operation. There's another nice thing from the inops, which I'm saying, so you have something that is shaped, the number of lines, that's 8 by 3 by 3. Well, if every single entry of that 3 by 3 is a true, that I want it to be true, that's an all command. So if they're all true, it's reducing. And it's reducing, it's taking out the row and the column operation. What do you have at the end? It's a ... comma, n lines. So n lines for this game is 8. In Pig-Tac-Toe, n lines is like 20 or something, because there's more 3 in a rows all over the board. Okay, so that's how these things work. And that is running it on several games at once. Okay, here are some more useful ones that you can do. Here is a very simple value function I made. This value function inputs one board. So its value, it inputs 1 board. And the reason it inputs 1 board is because it's doing this jnp.sum. So it's summing out the 3s. It basically counts up who has more 3 in a rows, and it's using the first parameter for player 1's 2 in a rows, or 3 in a rows, and the 3 parameter 3.0 for the player 2 3 in a rows. So that's my value function here. Let's copy and paste this up here into a little example. Okay, so that's my thing. And then if I do value of the first board, you see the value of the first board is 2, because player 1 has a 3 in a row, player 2 does not. What is the value of the second board? It's -1, because it's 2 minus 3, which is -1. Okay, so that's the value function. But as written, this value function will crash, or it won't give what we want if I do this. Does anyone think of what will it do if I just feed in both boards at once? So we would like it to say 2, -1, 2 for the 0th board, -1 for the first board. But what will it actually do? Let's run it. It outputs 1. So it added up what to do on all the boards. So it took the sum of the first board. We lost the information of which board is which. We've just crashed them together. There's a couple ways to fix this. One is instead of using sum, if I do sum with axis equals -1, now it's saying only sum over the end, and that will fix it. So that will restore it. You could also write this with a reduce. You could say reduce net 3s, and we know the net 3s is oh, look, it's written over here. Okay, this is the line that we want. So that's the same thing as summing over the last axis. The -1 means sum over the very last axis. So -1 means the very last one, but you can write that on words. You say ... n line, sum out the n lines to just give me a ... That'll be the same thing. So now it will work. But what if you're even lazier, or like your code is like complicated and you don't want to do it? Well, fortunately for you, there is a nice command in JAX called jax.vmap that will do it for you. So I'm going to put back the original version I had. So here is the original version that is doing 1 board at a time. And, oh, okay, wait. Here is the original version that's doing 1 board at a time. And if you feed in 2 boards, it just adds them together. That's not what we want. We want to do, so this works for 1 board at a time. How do I upgrade it to work for 2 boards at a time? There's a nice command called jax.vmap. So I'm going to make let's call it array value. And what you do is exactly what Google is suggesting, array value. You do jax.vmap of value. And very roughly speaking, what jax.vmap does, it says, when I feed in an array of boards, just run the value function on each board individually. But what you have to do is you have to tell it which ones have copies. And in this situation, the way to do it is like this. You say in axes equals none, comma, 0. That's the right thing to do. Let me explain what this means. So in axes always has to be the same length as the inputs. So I wrote 2 things because there's 2 inputs, parameters and board. And none means I'm not doing anything with those, just copy those over. They should be the same for everything. So I'm using the same parameters for all the boards. Maybe there's some situation where you want different parameters for board 0 and board 1, then you would change that. If you put 0 over here, that means the 0th axis of whatever I feed in here will represent different boards. So this is what we want to do, and that now it will work. So if I do boards, and I do it with array value, it does the 2 things individually, and it really is identical to doing value of params boards 0 and value of params of boards 1. So that is, I gotta print them, but other than printing them, this will be what we want. Okay, so if you do them, you get 2 and -1. And if you do the array value, because I said I'm going to parallelize over the 0th axis of this input, so I'm going to feed in a bunch of boards and just apply the function to all of them. And the nice thing is it works no matter how many boards you have. Like boards could have 100 different boards, it would still work. There's one very, very helpful place where this is useful in the program. Can anyone think of a situation where your program needs to deal with 9 boards at once or something? Yeah. Yes, in the Mac, right? So the way the moves are handled is it gives you the moves. It gives you an array of 9 boards, and because of the way I have vmapped this, it will work with 9 different boards. So here, let's make this one. I think I just have it over here. Okay, here we go. So yeah, okay. Let's do this one. Moves. Okay, so here are all the possible moves where, let's say, you did the move 3. So if I print out moves, it's this giant array. It has all the possible things you could do by playing a 3. Of course, in the real game, you never play a 3. But it's doing it for everything, right? And that is an array. Actually, here, let's keep things simple and do boards as 0. So this is like what you are doing in your program, playing a 3 somewhere on the board. Well, there's only 2 spots to play it at the end there. So 3 here. Okay. And now I can feed into params into, I can feed this into array value. So I can do array value of params moves. And even though moves contains a list of moves all stacked together, this will totally work just fine. And it will calculate the value of all the different moves. In this case, all the moves it thinks are 2. It's like the score of every single move is 2. Let me try making some extra O's over here. Let's make some extra X's. Okay, there we go. So if you play a 1, it turns out playing over here, you'll get 4 points. All the other ones are worth 2 points. And so this array value, it calculates the value for every single board in moves all at once. And as long as you can write a reasonable function for value, and as long as it works with vmap, so some things don't work in vmap. If you do really crazy code, it will yell at you. But if you just do very sane operations, vmap will work. And then you can copy it over, and now it can calculate the best move for all of these. You might be tempted to do this. So you might say best move index. Best move index equals, and you might do jnp.argmax. This is a very tempting thing to do. And in this case, it works. Let's write down best move index. It's 6. So it's saying if you're in this situation, the best place you can play is square 6. 0, 1, 2, 3, 4, 5, 6. You play over there, you get an extra 3 in a row, Bob's your uncle. There is a problem with this. If you do this, your code will not work, and you will sit there for hours and not know why. Where was it? So it worked in this case, but it doesn't always work. Does anyone know why it doesn't always work? Yeah.
If you have a lot of loser positions, the best move might be illegal.
The best move might be illegal. That's exactly right. So remember, we got the moves. That's all the possible moves. But legal tells you which moves are legal and which ones are not. And the reason I made it do this, moves and legal, is everything is always the same size. It makes it easy to parallelize. So it's kind of like harder if you do one game at a time, but you're going to see it's going to be worth it later. But we need to somehow tell it only take the argmax over the legal moves. And the best way to do this is like this. Replace the value with negative infinity wherever it's illegal. That's what I'm going to do. So let's call this the my values, and that'll be this. And then let's call this my values, or else neg infinity, and that will be, there we go. Hey, look at that. So if the move is a legal move, leave it alone. And if the move is illegal, replace it with negative infinity. So this jnp.where is like how you do if statements for vectors. And now we can do the argmax. So my values, or else neg infinity. And of course, in this situation, it's totally fine. It'll give us the same thing, but you gotta make sure you do that, or you're gonna play illegal moves. I think I spent half an hour last night debugging this in my code, even though I knew to be aware of this. I had some like subtle reason. It was just playing illegal moves. And the reason I found it is at some point I gave up and I was like, let me print out one game at a time and see what this AI is doing. And it was like, I played a move, and I'm like, hey, this is the same board as before. That means you played an illegal move. So yeah, make sure you watch out for that. Okay, so vmap, very, very cool. If you haven't done your homework yet, this might help you out with jax.vmap, so you can run all the boards at once. And then we're going to use jax.vmap to run all the games at once. So down here, I have a very simple AI. So here's the value function from before. Here's the AI that does exactly what I said. So it takes, of the legal moves, it takes the one with the highest value. This AI will work on one game at a time, and then you can vmap it. So here's my vmapped AI, where I vmap it, and then you have to do some fancy stuff with the key to make the randomness correct. How much time do I have here? Yeah, I have enough time to explain this. Okay, so if you just vmapped the AI, like you just did this thing, so 0, 0, 0 means I'm vmapping key, moves, and legal. So instead of just one set of 8 moves, or one set of 9 moves, and one vector of size 9 for legal, I have 2 of them for every game that I have. So in this situation, because boards is 2, then you have two of these things. But the problem with that is the keys are annoying. So you need to feed it a different random key for every game, and so I explicitly do that over here. So you take the original key and you split it into a bunch of different keys, and then you return that. So this AI will play on all the boards. So it says the best possible move is 6 on the first board and 4 on the next board. So this is how you upgrade your AI from running one game at a time to running multiple games at a time. That is what you're going to have to do for assignment 5 and the final project, is run basically all these AI algorithms on multiple games at once. That speeds it up by quite a lot so that you can get a reasonable AI at the end of the day and not have to wait many days. Okay, I think that's where we're going to stop. Any questions or comments? Okay, I'll be around for a little bit. If you have questions about the homework, feel free to come up. Otherwise, looking forward to see what you guys come up with by tomorrow. Okay.